Okay, so I gave you this question from the previous video. Look at this. Like I'm asking you about a new conditional probability. So our question started from conditional probability of like this form. Probability of defective batteries among domestic batteries. Probability of defective batteries among imported batteries. So condition is whether it is imported or domestic, and then we think about probability of defective. But I'm asking you the other way. If you know that a battery is defective, what is the probability that it was produced domestically? So you are changing the role of main event and condition, right? So previously the condition was about domestic, but now the condition is being defective. Then, so the condition is defective. That means you only use, among these four types, you use this and this. Non-defective batteries are excluded. You can remove them, delete them. You don't need them. You only use the first and the third group. And that means out of 40, there are 40 defective batteries. Out of them, 12 are domestic. There are 40 batteries that satisfy your condition, but 12 of them uh, satisfies your main event, right? So that is 12 divided by 40. So, or if you think about this table, 2 by 2 table, it's easy. Out of the first row, we only think about the first row. You are interested in this, right? This outcome. So 12 divided by 40 is 30%, which is simple. And I will do a similar process like before. I will go the other way and extract a formula from this procedure. Okay, we get 12 divided by 40 like this. And you know 12 was 2% times 600 and 28 is 7% of 400, right? So now then 600 came from 60% of 1000 and 400 came from 40% of 1000. And now you see where those numbers are from. All those numbers are 2%, 60%, 40%, 7% are given in the question, so you know where they are from. But once again, 1000 is the number you choose, number I choose, but it doesn't matter because it can be cancelled out. In the numerator and denominator, you can divide 1000 in the numerator and the denominator. You get the basic underlying conditional probabilities only. Conditional and unconditional probabilities only. Okay? This is the Bayes rule. Bayes rule. This is called Bayes rule, and it derives it like basically it's to convert the main event and the conditioning event, B given A to A given B, right? So that's how we calculate that. And by the way, the denominator is actually familiar. The denominator is what we just got here. This is the denominator. So probability A is the denominator, which is also simple. Bayes rule, yeah. So we got it from the previous formula, and numerator is also common, right? So like actually mathematical derivation is slightly different. I just went through like a longer way to show you the intuition, but actually mathematical derivation could be easier. Like the definition of conditional probability is this. So this is definition. And numerator can be written this way by the general multiplication rule. We learned it earlier, right? General multiplication rule. It doesn't require any condition. And the denominator can be replaced by the previous formula we just showed, right? I told you. So then we get this, then this Bayes rule. Okay. no matter what you do, in the end, it's the same thing, right? So if you are familiar with mathematical argument, that is a good. But if you are not, then uh, think about this, how you do it, like imaginary, counting. So this is the famous Bayes rule. And here is the last example of this chapter, application of the Bayes rule. So it is from my personal experience again. My son is now 8 years old, raising to third grade. But when my wife was pregnant, uh, there like when during the pregnancy, there are a lot of tests, screening tests, right? So one of the key screening tests during the pregnancy is like to test for like birth defects, especially genetic abnormality like Down syndrome or spine or brain problems. I don't know exactly. I'm not a medical expert, but suppose that there are some screening tests uh, you can get during the pregnancy, and positive results imply that the baby is at high risk of birth defects. Negative means low risk. So it's not the end of the world. Like I mean, it does not confirm the abnormalities, but it is detecting the probability, right? So that's the difference between diagnosis and screening. Diagnosis is confirmation. It's 100%. You have like I have a disease, then diagnosis is made. But if I'm at a risk of something, but that is unknown, uncertain, then we call that screening. Okay. So when my wife was pregnant, the result was positive. That meant my baby was at risk, higher risk of like Down syndrome at the time, right? So I don't know how it is calculated, but the doctor told me that. So then, at that time, me and my wife, what is the probability that we have to calculate, right? So we just heard that, like, so notation. D means birth defects, P means positive result, N means negative result. So we already got positive result, but we don't know whether my baby has birth defects or not. So given the situation, what is the probability we would be interested, right? What probability we have to calculate at the time? I already gave almost all the information, all the hint you need to calculate the answer, to get the answer. Yeah, first, the condition is what already happened is positive result. The screening test result was positive, so P already happened to me, to our couple. So P is the condition. Given that we are hoping for the probability that our baby does not have birth defects. So D complement. Given positive result, we wondered what is the probability that my baby does not have birth defects. Okay? So then, this is the answer. And then, at the time, it's a real experience. The doctor told us about how accurate the screening test is. I don't know why. Well, I don't know why the doctor tried to like intimidate us, like scare us. Like she said, this screening test is very accurate. Like so. So she said, I don't remember. Some test rate is accuracy rate is like say 99%, right? Detection rate is 99%, something like that. Oh, it's really scary, right? But we searched like after we come back home, and we find that the detection rate, the doctor gave us detection rate is 99%, but it was defined as the probability of positive result when birth defects exist. Then, how can you translate detection rate in our notation? Think about it. Okay, so the answer is, in the definition of detection rate, what is given is birth defects. If birth defects exist, what is the probability of positive result? So this part is condition. Birth defect is given as condition. So D should be the condition. The answer is this one, B. Probability of P given D, right? So detection rate is this, which is different from the probability we are interested in. Okay, so this is a famous kind of test, like in famous statistical terms. So depending on you have defect or not, your test result may be positive or negative. So if you have defect, your test result should be positive if it was correct. So we call this true positive. But if you don't have defect, still you may get a positive result because screening test is not perfect, right? Then we call that false positive. Similarly, if you have defect, still you may get negative result. That is called false negative. And if the negative is correct, then true negative. So this is what how researchers like communicate, right? So and they define the accuracy measures based on these notions. Like detection rate or sensitivity rate, depending on the literature, different terms are used. Detection or sensitivity rates are defined as true positive result if there was defect, right? And specificity or selectivity rate, a different way of measuring the accuracy is when there is no disease, what is the probability of true negative, right? So this is their definition. Like researchers provide accuracy measures in these terms in many fields, right? And my doctor did, right? So then let's think about this example. I put some numbers. Detection rate was, like say, probability P given D, which is 99%. Specificity is negative result given non-disease, non-defect, right? Which I assume 90%. So it looks like the screening test is really accurate, like 99% and 90%. It sounds like, oh, 90% it will be sure, right? I will show you, actually not. Additionally, I will assume that the defect is only 1% common. Only 1% of baby has the birth defect, like Down syndrome. So from this information, we are going to calculate the information I wanted. I already got a positive result. Then what is the probability of defect actually, given a different condition from these measures? I will not do this for now. So please use the method I showed you in the previous video, like draw a tree. And I recommend you start from 10,000 because the numbers are more extreme. So it is better to use 10,000 to start with. And try to calculate Z. Out of 10,000, how many of the observations will fall into Z? So it will take time. You need to bring a pen and paper. And please try this. And if you are confident with Bayes' rule, just you may use the formula. If you think you don't need to do the diagram thing, that's okay. Then directly apply the formula to find this. Okay. So stop the video now if you need time, and I will turn the page. Okay, I will start from 10,000